Hello, everyone. Good morning and good afternoon for some of you in the audience today. Thank you so much for joining us. I'm Abby. I'm the Chief Scientific Officer at Precisionary Instruments, and today is very special for our webinar. I'm so excited to host MariPen Yeatts today, who is our speaker. We have a special relationship with MariPen, her project in her lab. And her research, we have had the privilege of supporting through many years through a close collaboration. We have seen her work with non-human primate brains and also human brains now. And so MariPen is a PhD candidate in biomedical engineering in the laboratory of Taner Akkin at the University of Minnesota. And her work has focused on developing large-scale polarization-sensitive optical coherence tomography, or PS-OCT. And we like to say this 5 times fast. It's the tongue twister in our company now. And these are platforms to image primate and human brain tissue at micro-scale resolution and map the organization of axonal pathways. And as part of this work, her group they started using one of our off-the-shelf large diameter compressed-dome vibratomes, which is the VF800Z model. And we have gone on to work with her to design and create a customized large diameter compressed-dome vibratome to fit the entire human brain in order to generate high quality sections from large human brain specimens. Oh, MariPen, go ahead.
Technically, it's half of a human brain. It can hold an entire human hemisphere. Yes.
Oh, there you go. Entire human hemisphere. And hopefully that has allowed you a method and a piece of equipment to get accurate a way to get sections for accurate structural mapping across extended tissue volumes. So today she's going to walk us through the principles of PS-OCT and how this technology can be used for large-scale brain imaging. And she'll also discuss and show you how the compressum is used for generating the sections leading to PS-OCT. So MariPen, it is a great pleasure to welcome you. I'm going to turn it over to you, and thank you so much for your time today.
Absolutely. Thank you for having me. I appreciate everyone who showed up to my little talk, and thank you for taking the time. As I mentioned before we started the meeting official, if anybody has questions, thoughts, suggestions, need clarity on anything, feel free to raise your hand or interrupt me at any time so that I can get that clarity. That's what I mostly care about for our presentation, is that clarity. But without further ado from there, I can go ahead and get started in this presentation of what is polarization-sensitive optical coherence tomography, or PS-OCT, and how can it be used. In this presentation, I'm going to go over the general basics of what this optical imaging technique is, as well as what I've used it for personally in my lab. So, without further ado, let us begin. First, what is PS-OCT in general? PS-OCT is a type of interferometry. Oh, you can see my mouse. I forget about that. It's a type of interferometry, or an interferometer, which is basically a machine that measures the interference patterns between light waves from the reference and sample arm. So the way that this works is you have a source. It has an output frequency of coherent light that is then passed to the reference and sample arm, in which it interacts with a mirror in the reference so that it is a fixed known return. And the sample arm is obviously the light interacts with our sample, which here is a little brain because that's what I image is brain. When they come back, they combine in the fiber and come to our spectrometer where we can record then those interference patterns. So all of that is basically the interferometry side of this, but the extra special thing about this particular setup is that polarization sensitive part. So what is polarized light? Polarized light is light waves fixed at a single axis of propagation. So this is an image from Encyclopedia Britannica where you can see that before the light is polarized, its magnitude can go in any direction, any orientation to this axis of propagation. When it passes through this polarization filter, it comes out as just one particular direction, which I have also illustrated here as if you looked at this straight on, it would look essentially like you've got this wave propagating at 45 degrees, and there's no light coming at any other orientation out of that. That will be very important for later, but for the sake of understanding this technique, just starting with what is polarized light is important. So keep that in the back of your pocket for later. So we're back here, we've got the reference and sample arm, and we have this polarized light that we care about. Now, the specific thing about the PS-OCT that makes it different from regular OCT for that polarized part is this polarization maintaining coupler, or the PM coupler, where we actually make sure we hold on to that polarization state throughout the entire process, and then we were able to record it at our spectrometer and use that for one of our contrast calculations after that. So now that we have the general understanding of PS-OCT is an interferometer that also holds on to that polarization state of our signal, what is a birefringent material? The reason why this matters is because that is ultimately what we're measuring with PS-OCT, is it measures natural birefringence. So when you think about birefringence, the most common example that you're going to be, that is brought up or taught, is calcite. This is a picture of calcite, and you can see through it that this grid sort of looks doubled. So what a birefringent material is a material with two index of refractions. It's often due to an anisotropic crystalline lattice structure, which is a big mouthful, but it basically means you've got a crystalline structure that has, it's like one of those optical illusions where if you look at it one way, it looks like an elephant, and you turn it 90 degrees and it looks like a person. So that's sort of what's happening with light when it interacts with a birefringent material. And that's very useful for creating optical components and doing all kinds of measurements, but it's not just calcite that is birefringent. Also highly ordered tissue, such as retinal layers, tendons, and what I'm most interested in, myelinated axons, gives us that same kind of birefringent signal, where you get a fast and a slow axis because the index of refraction is different along or across. Everything making sense so far? Are we all good? I'm assuming the answer to that is yes if I don't hear responses.
Yes, it's making sense to me. It's good.
Cool. Again, if anybody has questions or concerns, feel free to stop me, jump in for clarity. But continuing. So that's the basic of birefringent materials, and that's the basis for what we're actually imaging to get our contrasts in PS-OCT. So this is what my images actually look like. This is an example image. These are the three of the four main contrasts that I typically actually produce from my data. There are more contrasts that can be produced, but at this time, this is what we're doing in our lab. That's what we've got going in our pipeline. We have reflectivity, cross-polarization, and retardance. So reflectivity, you can see these equations down here at the bottom, is the sum of the amplitude of both of my channels. The cross-polarization is just the amplitude of the second of my cross channel. And the retardance is a relationship of the arctangent of the cross channel's amplitude over the main channel's amplitude. Now, reflectivity is basically just what it says on the tin. This is the light that you get back. It's very good for determining what is tissue, what is background, where are your ventricles, and any other issues that you might have had with your imaging that might show up a little bit funny on one of your other orientations. The cross-polarization and the retardance are both measures of that birefringence that I was just talking about, which, as I mentioned, is a great way to highlight white matter. And you can see in both of these images that this right here, this structure is the internal capsule. It's highlighted as white because it is in fact highly white matter concentrated. You can also see the corpus callosum right here. You see it in both. These two both highlight birefringence, but in slightly different ways based on their calculation. But fundamentally, they're both doing highlighting white matter. So these are my general contrasts. This is generally what we're outputting from my system. But you may ask, how do I get these beautiful images from an actual tissue? If I had a whole brain and I'm like, okay, cool. How do I get these pictures? Let's talk about how we prepare the tissue for the compressome and for this imaging. So this is the technique that we've developed in our lab to properly embed large tissue samples to try and get the best cuts with the compressome. So it is a three-step process. The first step is you will inject liquid agar gel into the large sulci and spaces in the brain. So in this particular image example, you see that using a blunt tipped syringe, we inject this agar gel, liquid agar gel, into the space between the occipital lobe and the cerebellum, which is just a notoriously large gap that's hard to section because it's very difficult to get the embedding medium in there. So this is how we get around it. We just inject it in there directly before we do the next step. And when I say liquid agar gel, this is low point melting agar gel, which is available through Precisionary or through other retailers. And the percentage will vary depending on which tissue you're interested in doing. And we can come back to percentages of the agar gel if that's something of interest. But carrying on, after we've gotten the injection into the large sulci, into large gaps in the tissue, we will then place it into a mold that we've custom made such that it will hold the brain in the desired slicing position. So this example shows it in the coronal position to make sure that we're going to have a nice flat bottom that we can then attach to the plunger in the next step. After we put it in the mold, we pour more liquid agar gel over it so that it will set in this position. And once it's set, we demold it. After demolding it, we then take this block that has the tissue embedded in it, put it into the compressed foam sample tube or specimen tube, and super glue the bottom of it down to the plunger to make sure that there's no rotation, there's no movement of the tissue during imaging and sectioning. It's very important for our images to continue to be aligned throughout the imaging process. And once it is embedded and fully set and cooled, we can then proceed with slicing. And the way that PS-OCT works is it does look in depth, but it can only see down about a half a millimeter. And I section at about 200 microns to make sure that I don't have strong decay between my sections for reconstructive purposes later. Once we've done all this, so one other minor point of clarity is that the imaging step happens between these two, basically. So before I slice, I will image, and then I slice, and then to save that slice, I put it into this custom designed and built 3D printed tissue storage system so that they can lay flat and be hydrated with PBS, because that's what I image in, and we want to keep the tissue obviously hydrated for future histology. This is generally how the preparation goes, and tissue from beginning to long-term storage. Now, besides this, let's look at the actual imaging setup itself. So this is a video of an actual slice that I imaged and recorded. It's sped up by 50 times, and you can see that the way that it works is we tile. So this is my scan head, and I'm imaging each little section of this brain, and you're seeing them be reconstructed over here on the right in what I call a real-time interface. This is a quality control measure to make sure that while I'm actively imaging, it actually is coming out correctly. I'm not getting weird vibration artifacts. I don't have like a water drop on my lens messing up my picture, anything like that that would cause this data to be unusable in the long term if I didn't know that it was happening. Now, this is again a coronal view. I have also done this with the sagittal view of the macaque brain, but I do not have those images in this presentation for the sake of brevity. Now, what you're going to see here in just a moment is it will finish doing the scan, and then you're going to see the vibrotome cut. It's going to be a bit of a jump scare because it'll be real fast because it's 50 times sped up. But this is how we're able to do the serial imaging of the brain for the entire brain. No, don't play again. I need to go to the next slide, please. There we go. Now, this is actually sort of the fanciest thing that I've got going on for my PS-OCT and the thing that people are most interested in. This is what you would call the optical axis orientation contrast. So what you're seeing in this image on the left is these colors represent the orientation of any given pixel or any given fiber in that pixel from negative 90 degrees to positive 90 degrees. So basically the full spectrum of 180 degrees. You can see this little color wheel down here to give you a good sense of what direction the fiber is going. Where if you see this like purple pink color, that's basically around positive 60 degrees. And as you go towards the teal color, it goes down to 0. 90 is red at the full up and down. And it's a circle. So it can circle all the way around for both halves of, whoops, sorry about that, both halves of the unit circle. Now, this is calculated by getting the change in phase between my two channels, my main channel and my cross channel. And you can only do that phase comparison with the polarization-sensitive optical coherence tomography. Otherwise, you don't actually retain that measure and you won't be able to get this output. So this is a nice big overview, but let's do a zoom in and actually see some of the power of this technique. So we're going to zoom in on the globus pallidus, GPI, GPE, but that's what we're looking at, this slice. And you can see here there's a lot of beautiful detail that you can see going in and through these areas. And again, what's highlighted is bright in color is white matter. The background is darker because it has less birefringent material in it, so it has a weaker signal. And you can see that there are these beautiful different orientations of these structures going through the GPE, GPI, as well as the fibers coming out of GPE, GPI. Over here, you can see the edge of some Wilson's pencils. And all these orientations are based on this circle. And the other great thing about this is these are not estimated orientations. These are measured orientations and calculated orientations based on the actual optical properties of the fibers themselves. So this is kind of that nice, beautiful money shot of a specific zoom in that most people are interested in. An example of something else cool is you can see right here, there are crossing fibers. That's another thing that's pretty powerful about this technique is you can see this pink fiber is going through and crossing this green fiber bundle. And you can very easily distinguish them with this orientation contrast. So, and the final thing I'll say is this is something that I'm working on in collaboration with other labs. This is a PS-OCT cross-polarization image, and this is the corresponding high-field MRI FA map of the same location in the same brain of the same animal. And this overlaying collaboration and further tractography reconstruction is being processed, but that is outside the scope of this presentation. I just wanted to let you guys know that it is a great combination of multimodal imaging that we are working on. And here are the acknowledgements of my grants and the people in my lab. And thank you so much for your attention. I am now open for any questions, suggestions, or further inquiries. I hope this made sense and was interesting to everybody.
Yes. Thank you so much for taking us through and for developing the technique for imaging and explaining it. So I do want to open up to everybody and see if you had any questions. And please feel free, we're a small group, so feel free to show your video if you like and unmute. Or put your question in the chat box. And
also, I'm just going to throw out there, Saad, is that you? Like, is this the Saad that I know?
Hello. Someone
Hey,
sent me this
Saad.
invitation, so I clicked on. I'm glad I came. Really great presentation.
Yeah. Good to
Hi,
see you.
everybody. I'm Saad.
Hello, Saad. I like this. It's a small group reunion in a way. We just had one comment for you, MariPen, which is these are spectacular images, and they truly are.
Thank you so much.
Yeah. And don't worry if you all don't have any questions, but think of others later. Reach out to us at info@precisionary.com. We can put you in touch with MariPen if you're not in touch already. And we can always go from there.
Mm-hmm.
Yes, Saad.
I have a question. So in some of the images you showed, beautiful images, but sometimes you could see some artifacts. I was wondering if you're able to go back and reacquire or go back and fix those things, or are those unsalvageable parts of the brain?
So which artifacts are you specifically asking about?
Not specifically on these pictures, but
on other images you've seen before?
I guess near the cortex, maybe those are
yeah, so in this particular data set, there's a couple of artifacts that you can see. One that you can see very clearly in this reflectivity is this right here. That's actually a blood vessel that's come up through the solstice and didn't cut properly with the compressome because they're hollow and they tend to just like smush out of the way instead of cut. It can be a bit difficult to get them to cut in general with any technique. It's not dependent on this particular compressome. It's just they're fiddly. And if we're not careful about it, then they can get a little bit long and cast shadows on my image. If that happens, I unfortunately do not have a way to recover the data that would have been under that, because that data just wasn't recorded.
And you mentioned when, as you acquire the data, there's tiles appearing for quality assessment.
Mm-hmm.
So do you actually encounter issues while acquiring, and are you able to fix them on as you go?
Yes. So when I say, no, it's the other way. When I say that there are issues in acquiring, if I skip ahead, please. Pause it. If you look here, you can see that right here on this image, it's a bit dark on the top of the thalamus. This is actually a cutting artifact. So the reason that it's dark is because the surface isn't completely smooth and flat. And when we have issues like that, that can distort our data or give us errors in our calculations, depending on how bad that distortion is and depending on which contrast you're talking about. Now, when I see errors like this, if it's an error where this surface is too high, then I can potentially run the compressome over at a very small thickness, so it doesn't really raise, and I just smooth that surface out again or further. But if it's a divot, I can't really fix that. The other thing that you don't see as an artifact in this particular slice, because it didn't happen in this slice, is if the table gets bumped while I'm imaging, there can be ripples in the water in the PBS solution, and I will see those ripples in my images and they will mess them up. And that's one of those things, like if we're recording, that could happen for a single tile but not show up on any other tile. And if we can catch it in this phase, then we can just re-image the slice before we cut it. Once we've cut the slice, it's done, and re-imaging a slice is very, very difficult.
MariPen, this is obviously sped up. To get a whole image like this, what is actually the real time for this?
So that's been something that we've worked on a lot, and it has changed over time. For another point of reference, so you guys know that this brain that I've been showing you, this is the first brain we actually did cut an image. So it's a little bit uglier than the newer brain that we got as far as the quality of cuts go and the consistency of everything across it. So a lot of these errors that we saw with this animal, we were able to resolve by improving our techniques for the second animal. But this animal has still got good data and is still generally very good and important. The actual speed of this, though, is roughly, depending on the size of the slice that you're doing at a time, how many tiles you're imaging. So like, for example, this particular tile, I think is somewhere around like 99 tiles. So 99 little fields of view that I'm imaging. Doing a slice this large takes in the ballpark of 45 minutes to image.
Okay. Wow. That's still pretty amazing. Yeah.
Yeah. But for considering the amount of data we're getting out of this and the resolution of about 10 microns, it's still pretty fast. We're working on trying to make it faster by streamlining our saving process, and reducing the amount of data that we're saving, because this picture here on the left is a full depth profile. So this is the entirety of data that we're saving, where we only actually need this small amount near the surface of the slice. So a lot of this is not needed, but we just save all of it right now.
Sure.
So that's another way to speed it up.
Very nice. Thank you.
Hey, Sam.
Hey, can I ask a question?
Go for it.
While you have this cool slide up, can you explain what all the four graphs on the left are showing?
Yes, I absolutely can. So starting with this, so this graph all the way on the left is what we call an A-line. So if you took one measurement that you're saving from the camera, like one basically snapshot of the camera that we have, it's a line scan camera at a time, it's this A-line. This is the amplitude of the reflectivity. So this is basically the intensity of light I get in depth, and this bright spot right here is actually my reference line. We use that for dynamic orientation offset calculation. And then on the right of that, what you see is if I take these A lines for every single part of the scan and I line them up side by side, that's what gives you my depth profile. So you can see the surface of the tissue is here. This is the surface of the gel right there. And I did pause it on a very ugly section around the cerebellum. So this is why it's so ugly and jagged. But usually it's very, very smooth. This is just not a great beeline. But that's what a beeline is, / what a depth profile is. And what you're seeing here is the reference line, the actual tissue signal, and then these other lines are reflection artifacts of the system. And it's impossible to completely eliminate them, but we do remove them in our post-processing via background subtraction that's calculated from a given tile. This bottom part of the signal is not necessarily of interest to most people, but it's important for us. This is actually what our raw spectral data looks like. So this is actually what's being saved when I save data. This is the more comprehensible visualized version after we've done the FFT. But this is actually what our raw spectral data looks like, where you've got the pixel number on the camera versus the intensity. And you can't see it because it's zoomed out. But what you're seeing is a general curve shape of what our spectrometer picks up. And then the variation on it is what the actual signal is. To the right, this is my real-time in-face. So this is basically a big matrix where I'm dumping all of my in-face images in. And when I say in-face, that's, I take the average in depth. So I'll basically say, hey, go from like pixel about 50 to about 150. So from here to here. Just average those to generally give me an idea of what my signal looks like. And that outputs this. And this is basically the compilation of these. So as I'm going, whatever tile I'm on will show me here. And then it will pop up in here when it's done. And while the next one is scanning, I'll have the previous tile visualized until we go to the next one and it will switch. So those are the graphs that you can see in this image. Does that make sense? Does that answer your question?
It sure does. Thank you.
Awesome. And I just wanted to make a final call out for any additional questions or comments. All right. If not, I just wanted to thank you, MariPen, for your webinar, for sharing your process and data with us. So any other questions, let us know, and round of applause. Thank you. Yes. All right.
Oh, one other thing for clarity, just because I didn't really showcase it here. Mm-hmm. I do have these same in-face images for the entirety of this brain, from tip to tail, basically anterior to posterior. I've only showed one slice in this presentation for the sake of brevity, but I do have all of the slices of this brain if there is interest in that. That will be going out in a publication very soon.
Wonderful. And when it does, I know for sure that Precisionary will also be announcing it as well. So look for that. Thank you so much, everybody.